Today we are learning the Bronsted-Lowry definitions of acids and bases so that we are able to accurately identify when chemicals act as an acid or a base. And our success criteria is being able to define acids and bases as proton donors and acceptors, and being able to identify Bronsted-Lowry acids and bases in a reaction. So these are the evolution of the Arrhenius definitions that we learned in Chemistry 20. Johannes Bronsted and Thomas Lowry, instead of focusing on the properties of acidic and basic solutions, tried to predict when chemicals will take on the role of an acid or a base. In these Bronsted-Lowry acids and bases, water is still present. But unlike the modified Arrhenius definitions we used last year, water is no longer necessarily a primary reactant. Water can still act as one of the chemicals in a Bronsted-Lowry acid-base reaction, but it doesn't have to. So we're no longer defining acids and bases based on their relationship with water, but by how they're able to react with other chemicals. So the way the Bronsted-Lowry definitions work is that a Bronsted-Lowry acid, or a BLA, is any proton donor. A Bronsted-Lowry base, or BLB, is a proton acceptor. So they defined acids as chemicals able to give away protons or hydrogen ions, and bases as chemicals that were able to accept protons. And then a neutralization reaction is just a competition for protons, where one is being pulled away from an acid and being accepted by a base. So really, all Bronsted-Lowry acid-base reactions are some form of neutralization, just like other acid-base reactions we've learned about before. But instead of being between this strong acid and a strong base, we can now include weak acids and bases in these reactions. So it's just the strongest acid or the strongest base. And we should note as well that there are some chemicals that we classify either as amphoteric or amphiprotic. Both of them mean the same thing. What it means is that these chemicals act as acids in some situations and act as bases in another one. In fact, we already know one of these. Water is the most common amphiprotic substance. In some cases, it can act as a proton donor, giving away a proton, and in some cases, it can act as a proton acceptor, receiving a proton. So in one situation, it acts as a proton donor, and in another situation, it acts as a proton receptor. We should note, though, Bronsted-Lowry definitions do not explain why the proton is donated or accepted. This is not the most modern and most refined definition of acids and bases. However, we don't deal with the more refined definitions, the Lewis acids and bases, in grade 12. That is usually left for university. And even though these are not the most in-depth explanation possible, they are still a very, very good definition. So for high school students, they're good enough. The advantage of using these Bronsted-Lowry definitions is that now we can define acids and bases in terms of the chemical reactions they have, instead of just defining them as, oh, this one turns red litmus blue, so it must be a base. We're getting away from the properties of acids and bases and more towards a definition based off of what the chemical is. On top of that, we have something called a conjugate acid and base. Whenever a Bronsted-Lowry acid or base reacts, it turns from an acid into a base, or vice versa. And we call these created chemicals and the products the conjugates. And you'll notice in an acid-base reaction, the Bronsted-Lowrey acids and bases are always going to be in the reactants, and the conjugate acids and bases are always going to be in the products. And these actually work the same way. A conjugate base is a chemical that is going to be capable of accepting a proton, and it is paired with the Bronsted-Lowrey acid. So the example I've given in here, both in text and in the diagram below, is of acetic acid, hydrogen acetate. Acetic acid is a Bronsted-Lowrey acid because it's able to give away that last proton. But then the acetate ion is acetic acid's conjugate base. So this creates what we call a conjugate acid-base pair. It's two species that have the exact same formulas, except they're separated by one proton. So if you want to take a look at water, a common conjugate acid-base pair for water would be the water molecule and the hydronium ion. Or you could also make a conjugate acid-base pair out of the water molecule and the hydroxide ion. But you could not make a conjugate acid-base pair out of hydronium ion and the hydroxide ion because they're separated by more than one ion. Just like when we talked about oxidizing and reducing agents, we can quantify acids and bases in terms of strength, and a lot of what we do in this chapter will be doing those quantifications. The stronger an acid is, the more easily it wants to give away its proton. The stronger a base is, the more it wants to steal someone else's proton. Works actually very similar to what we looked at with electronegativity in grade 11. We can also represent general formulas for Bronsted-Lowrey acids and their conjugate bases. We often will use HA as the general symbol for an acid and A- as the general symbol for a base. And the reason why you use that specific formula is that that creates a conjugate acid-base pair. They're separated by a difference of just a single hydrogen ion. The extent to which the acid wants to give away its proton is what determines the relative strength of that generalized Bronsted-Lowrey acid. And you'll also notice that the relationship between the acid and the conjugate base is inverted, or between the base and its conjugate acid. The stronger the acid is, the weaker the base is. And the stronger the base is, the weaker the acid is.